the demand for safer, more efficient, and scalable battery solutions grows, simulation is becoming a strategic enabler. For electric vehicle battery packs, virtual modeling of battery behavior facilitates faster, safer, and cost effective development. Today, I am speaking with subject matter experts from MathWorks to explore how data and AI powered simulation tools are enabling engineers to model and optimize battery systems with greater precision and speed. We also look forward to hearing a few user stories and real life examples of their implementation. I'm glad to welcome Danielle Chu and Prasanna Deshpande from MathWorks to EV Reporter podcast. So Danielle is a product manager at MathWorks, and she specializes in power electronics and battery systems. And Prasanna is an application engineering manager at MathWorks India, and he works closely with automotive OEMs, suppliers, and startups adopting model-based design. Thank you both for joining me today.
Thank you.
All right, so let's get started. So for companies producing battery packs and BMS, why has simulation become such a critical enabler for them today?
So I will give you some background about the simulation. So MathWorks provides the block diagram environment that lets engineers perform system-level multi-domain modeling like electrical, mechanical, and digital control, such as the full powertrain, and component modeling, such as the battery pack, and the algorithm development, such as the battery state of charge estimation in the BMS. So by running the system-level simulations, engineers can understand the interactions inside the system. Then engineers use Simulink to model the powertrain of an electric vehicle and MathWorks optimization toolbox to identify the battery pack size so that the electric vehicle meets certain range and cost targets. So once you know the battery size, and then you can use a SimScape battery to model your battery pack and your BMS algorithms, such like I mentioned, state of charge estimation, state of health estimation, and cell balancing. So these level of details and control algorithm designs, so you need to create the right level of physics that give you the battery behavior, including the thermal behavior. Then you can design your control algorithm in the same environment. So using the same models in Simulink, it can be also used to generate the C code and HDL code for hardware in the loop testing to further validate your BMS algorithm in real time. So your battery models are ready. You generate code from the battery models and deploy the code to real-time target machine, providing a virtual real-time environment that represents the battery pack, and the active and passive balancing circuit elements, the load, the charge, and other components. So in this context, the real-time means that the models on the real-time target machine run at the same rate as the actual physical system. For example, if the battery takes 30 minutes to charge from 60% to 80%, it would take 30 minutes to charge in the real-time simulation as well. So this virtual environment lets you validate the functionality of the BMS controller in real time before developing a hardware prototype. And based on the real-time simulation results, you can verify and refine your BMS design. So it's actually an iterative process. So for example, you may go back to change your state of charge estimation algorithm in the models, regenerate the code, and test again on the hardware in the loop system. So by the time you go to actual hardware testing, the algorithms are more mature. So engineers spend less time on testing with the real hardware. So you may spend more time upfront on the simulations, but the testing on actual hardware will be more likely successful and quicker. So at the end, the development cycle is shorter.
Thank you so much for that comprehensive overview of the tools and what battery modeling and simulation can do for BMS engineers and battery engineers. So, coming to battery modeling specifically, can you help us understand what is the importance of cell characterization in battery modeling and how do engineers ensure that the model aligns with the experimental data?
Thank you for the follow-up question about the cell characterization. So engineers, when they model the batteries, they and first question will come to mind: what are the parameters inside of my model?
Right.
How accurate my models representing the actual battery behavior? So cell characterization is the process of fitting a battery model to experimental data. So accurate cell characterization is important because the BMS algorithms use the battery model to set control parameters, such as those of a common filter for SOC state of charge estimation, or power limits based on the state of charge, or temperature to avoid the overvoltage or undervoltage conditions. So by fitting a battery model to the experimental data, engineers can enhance the accuracy of the simulations, so which lead to a better BMS design. However, for successful cell characterization, engineers should follow a structured approach to the data collection, model selection, parameter fitting, and validation to ensure that battery models reflect the experimental data correctly. And here are some steps. For the data collection, engineers need to decide what tests to conduct in the battery test lab and collect the data on voltage, current, temperature, and state of charge during the charge and the discharge cycles. For testing, typically current profiles need to excite the battery system adequately so that there is enough information for identifying the battery model parameters. These are typically made of pulsed current profiles. An example can be like HPPC, hybrid pulsed power characterization profiles. Then the second step is battery model selection. There are different types of models to model batteries. So engineers need to choose an appropriate battery model that can be parameterized to fit the experimental data. And the choice of the battery models affects the complexity and accuracy of the simulation. So it must align with the intended application and available data. Some common model choice include battery equivalent circuit models, electrochemical models, and data-driven models, which are based on AI techniques. The battery equivalent circuit models is often employed for BMS design because of its simplicity, high fidelity, and computational efficiency as well. Then the third step after you choose the battery model, next you need to fit in the parameters. We call it a parameter fitting. So engineers using techniques such as curve fitting, optimization algorithms, or machine learning, engineers adjust the model parameters to minimize the difference between the model's prediction and the experimental data. So precise parameter fitting makes sure that the model can accurately predict the battery behavior and a wide range of conditions. Then after you parameterize the model, you need to validate the model, the accuracy. So engineers validate the fitted model by comparing its prediction against additional sets of experiment data. So this data would be a different data from the parameterization process. So it may be a drive cycle current profile that are not used in the fitting process. So it's a different set of data. Then it's again, it's an iterative refinement. So based on validation results, engineers may iteratively refine the model by adjusting certain parameters or incorporating additional data to improve its accuracy. So cell characterization is a fundamental process that enables engineers to develop battery models closely aligned with the experimental data. So by following a structured approach to data collection, model selection, parameter fitting, and validation, engineers can create a highly accurate models that enhance the design of BMS.
All right. So, an accurate representation of the battery pack in the simulation model is necessary for an end-to-end BMS development workflow. So, what features do MathWorks tools have for making it easy for battery engineers?
Yeah, that's a great question, Priyakshi. Uh, Daniel just now spoke about two main things. One, which is a recent answer, which was on cell characterization, which is a very important and fundamental thing, so that we ensure that real world data is represented in the battery cell. And in the answer to first question, she also explained what you are referring to in this question, which is end-to-end battery workflow. I'll not get into the workflow now. I'll get into the tools which are allowed, which can be used for and realizing these workflows. One very important thing that we have is, and I'm not taking tool names, but there are a few beautiful apps that we have developed. So one app is on battery pack model builder. So this battery pack model builder basically automates the creation of battery pack architectures, including cell, module, assembly levels. You can include the thermal plates, cooling plates. So it allows you to interactively design your battery pack once you design your battery cell. So battery cell characterization workflow, it's for the cell, and how you convert that cell to a battery module and battery pack. There is an app which speeds up and automates the process of battery pack building. It also, in a sense, it also helps you to do 3D visualization, like inspect geometry, layout, and thermal interfaces. That's also possible. Then next is for different use cases through the end-to-end workflow of battery and battery management system development, you need multiple fidelity components of your battery pack. There is a tool called Simscape Battery, which allows you to have customizable fidelity of your battery pack or of your battery cell. You can choose between fast, low fidelity models for early design stages, or you can choose high fidelity models for detailed analysis. So that's another thing, which more fidelity means more accuracy, but it also takes more time to simulate. And lesser fidelity means the model will simulate fast, but it won't have a lot of details modeled with as a part of that variant. So you can actually switch between different fidelities based on your use case. So that's another good thing. What is also important and deserves a mention is thermal coupling. You can easily integrate cooling plates and simulate cell-to-cell temperature variation, which is really important for Indian conditions. And also, this tool gives you BMS block libraries. If you remember, Daniel was mentioning about SOC, SOH estimation, fault detection, and balancing. So we do have readily available blocks for these in Simulink platform, which can be used as a starting point models. You can get started by using these blocks by putting them into your BMS architecture model and then start parameterizing them. So that's how you can analyze the workflow that Daniel spoke about, which is rapidly iterate and test your control strategies, perform agile validation in a unified environment. What is also possible is once your BMS battery management system algorithm is ready, you can use the verification and validation tools to validate your algorithm. What I mean is, one is functional testing, which can certainly be automated. However, more than that, what is also possible is you can do design error detection. You can get into the algorithm and check that there are no dead codes, there are no dead parts in the model which are not there. There are no errors like divide by zero, which is also important when it comes to a safety critical function like battery management system. So I think these are the different features available with the MathWorks toolchain for battery and battery management system development.
So I'll come to emerging markets like India. We see a lot of EV penetration is happening in two-wheelers and three-wheeler space. A lot of them are being used in very demanding use cases. So we feel that the overall the vehicle and as well as the battery pack, everything needs to be very rugged and well tested. So specifically for these vehicle segments, what kind of support do you provide?
Yeah, thanks for this question, Priya. Actually, this one is very close to my heart, and I'll tell you why as well. So yeah, as far as 2-3 wheelers are concerned, I think you said the challenges very correctly. It is tight packaging. It is a very cost competitive market, so there are a lot of cost constraints, and also the usage patterns are diverse. Like one segment is urban segment, which is a lot of traffic. The other segment is uh, not so great roads. So we have to design vehicles which will take care of diverse usage patterns. This is where simulation helps manufacturers to address by enabling virtual prototyping and optimization. So I'll go back to the end-to-end. I'll just scale up the end-to-end battery management system workflow to end-to-end electric vehicle management workflow. It's the same workflow. Basically, simulate drive cycles tailored to urban or rural conditions, optimize your component sizing. Now, not just battery, but the battery, the motor, the controller for your goals, which could be a trade-off between performance and cost. Then develop and test control algorithms. There are different things when it comes to vehicle, like regenerative braking. As far as two-wheelers, three-wheelers are concerned, ABS systems are also important. Thermal management in India is always important. So these things are really important. Ultimately, simulation enables these OEMs to deliver reliable, efficient, and affordable EVs, which are tailored to local needs. Now I'll come to the part why I was saying it's my it's close to my heart. There are two examples where which I would like to quickly bring. One is on Ather Energy. I think everyone knows Ather Energy. They are in a sense pioneers in electric two-wheeler industry in India. So this Ather Energy team, they needed to run simulations to evaluate design concepts for a variety of riding and usage scenarios, and they wanted to make uh, trade-offs, but in an informed way. So they wanted to have design rationale for all their design trade-offs. So what they did is they built a battery system level model, and they used it for different use conditions. I'll tell you one of the classic example. Not just Ather, a lot of people face it. See, increasing battery capacity would provide better range, but it also increases the cost and size, as well as it affects the scooter's center of gravity. So how do you balance that trade-off? What is the right size for my use case, right size of battery for my use case? So building a vehicle plant model of the scooter, or a plant model means vehicle component, vehicle system model of its main components, along with vehicle dynamics, mechanical components, it helps you to do these kind of design trade-off studies. And what Ather did is they used first principles approach for building most of their components in the absence of detailed component data. For example, battery. Their team took an empirical approach to modeling battery cells. Next, they developed the algorithms for battery charging, for power control, for temperature control in Simulink. They connected their vehicle system models and control system models. They ran closed loop simulations to validate their control design. And once they were happy with their control designs, they also generated code from the controller model by using embedded coder, and then deployed it to their ARM Cortex processor and TIC 2000 controller for different use cases. So why I went into so many technical details, the benefit that Ather team got is they could design alternatives in weeks. Typically, it is done in months. Their testing time got reduced by almost 50%, and field issues also rapidly resolved. One more thing about Ather is Ather Energy is a startup company.
Yeah.
And they got benefited by the startup license that MathWorks has. So MathWorks has dedicated initiative to promote startups, to promote usage of MATLAB in startups. So we actually give them, there are certain conditions, certain star marks, but to a few startup companies who are incubated at a specific incubation center, they do get some complimentary access of MATLAB, all our tools. Later, there are separate startup suites available for them to use. While they're using startup suites, they do have access to the complete MathWorks ecosystem, along with MathWorks technical support, and our application engineering team also works with them.
So I'll also talk about artificial intelligence. So if you could help us understand what role does AI play in enhancing the performance of MathWorks solutions?
So with more data, large data available, indeed, MathWorks provides AI-based workflow for both battery modeling and the BMS design, including like battery state estimation, state of charge estimation. So engineers can create AI-based reduced order models using, MathWorks has a reduced order modeler app. So use this app to create reduced order models for the battery when the engineers have large amount of data sets available, either from very high fidelity simulation models or experimental testing data. And these AI-based model can be integrated into Simulink for the system level simulation, like we mentioned earlier, generating the C code as well, and performing hardware in the loop simulation. For the state estimation, battery state estimation, engineers can use the AI techniques like a deep learning toolbox from MathWorks to estimate the battery state of charge. So the AI solution more like a virtual sensors to estimate the temperature inside of the battery, and also can use to predictive maintenance toolbox to predict the remaining lifetime of the battery. So which is important to give the customers and engineers how much life remaining in the battery. All those models can be, like I mentioned, deployed to real-time target machine as well for the virtual real-time testing.
I wanted to add one quick example we have
Yes.
here also. So we have worked with KPIT. KPIT is into a software integrator into automotive domain, and a very interesting presentation they have done in one of our conferences is KPIT could use deep learning tools, so deep neural network approach for doing SOC SOH estimation for the BMS. Why they did that is because a lot of times, a lot of people find the traditional approaches, which are like Coulomb counting and Kalman filtering based approaches, little complex. So KPIT used deep neural learning based approaches, and they actually got very good accuracy in comparison with traditional approaches. So again, advantage of model-based design is they could compare traditional approaches with deep neural network based approaches. So AI-based approaches. Not just that, but they could also deploy their AI algorithm onto an embedded platform. So that's also a very good win. I think they were using a embedded platform from NXP at that time. I'm not too sure about it. But yeah, we do have a presentation from them in one of our conferences.
So coming to another critical aspect of battery systems, thermal management, that's crucial for battery safety and also battery performance. So as electric vehicles become more complex, especially with shared thermal systems, what are some challenges in thermal system development and how does simulation help here?
Yeah, I like the term you used, shared thermal systems. So you're right. Thermal management is not just about cooling batteries, but all these electric vehicles have shared thermal loops for batteries, motors, power electronics, and cabin HVAC as well. So that's basically a complexity. So these challenges include we need to balance the heat load, we need to manage the energy efficiency under varying environmental conditions, because if it's a trade-off between I'm driving in hot condition, my battery charge is low. So should I give priority to keep my cabin cool, or should I give priority to reaching my destination? So the vehicle control unit needs to take a lot of different decisions like this. It is also safety critical. So you need to ensure safety during fast charging and extreme weather related conditions. So this is where simulation helps you in building multi-domain systems. So you can build battery electrical and thermal systems. You can build battery management and battery thermal management systems. You can test them together. You can test them for different scenarios like cold start, high speed driving, cabin cooling. You can also test different optimization workflows to minimize energy consumption and maximize range and things like that. Of course, we do have tools and workflows for doing that, but I'd like to share one experience. Mahindra and Mahindra use MathWorks tools to create a flexible real-time simulation setup that allows their engineers to test and improve EV thermal system controls even before the ECU is available, making the development faster, efficient, and cost-effective. See, now electric vehicle thermal systems must operate with high efficiency to enhance their range and performance. And effective control of various thermal components is essential to minimize that energy waste. So that is where it becomes a lot of times challenging to really get into designing and validating your thermal controls while the complete vehicle system is in process, while the complete vehicle system is in development. So the benefit Mahindra got was their timelines for development of electric vehicle got reduced. Tough to test strategies. They could test these strategies without having their production ECU with them. They have developed a real-time test platform for testing different strategies and logics by leveraging rapid control prototyping using MATLAB and SpeedGoat. SpeedGoat is a rapid control prototyping environment. So in general, faster time to market, reduced development cost. That's about it.
So skilling is seen as a significant challenge for the overall electrification ecosystem. So how is MathWorks helping the EV industry build and upskill its workforce to meet the growing demands?
Yeah, I agree. Skilling is a big challenge for Indian automotive industry. I'll just cite a report. Society for Indian Automotive Manufacturers, CM, they have a report written on EV talent landscape in India. And as per their report, there is a forecast that India will require between 1 lakh to 2 lakh skilled professionals, including engineers, scientists, and technicians, to meet the 30% EV adoption target, which is set for 2030. So by 2030, we'll require 1 to 2 lakh skilled professionals. So what, and within this, they have also done an exhaustive study in terms of, 43% of EV related technical competencies have minimal overlap with the existing ICE, like internal combustion engine skills. Then 27% have high overlap. So they may need a little bit of reskilling. So we need to ramp up about 15 to 30,000 EV ready workers per year to meet our 2030 goal of skilled engineers. So that's pretty huge. So now coming to answering the question, MathWorks does have several initiatives for helping professionals as well as students upskill their electric vehicle skill. We in fact do have a web page with title as Upskill for the Electric Vehicle Transition. I'll be happy to share that with you later. So see, it's about different things. It's not just about tool competency. It's about competency on the technology. So we do have a video series for things like motor control, for things like battery management system development. We do have readily available models, which can be used as starting point models for people who have access to MATLAB. Then in terms of tool competency, we do have free on-ramp. On-ramp course is basically anyone can log in and take that course by using online versions of MATLAB and Simulink. Then we do have instructor-led training. MathWorks does give a lot of value to engaging with universities, engaging in academia, and we do have several pre-developed curriculums, or we do develop several curriculums along with universities, along with industries and universities as a joint venture. And we are actively helping industry academia to bridge that gap and to make more and more engineers ready for with EV skills.
All right, that's really interesting to know, and we'll be sure to put out some of those links on this video. So thank you so much, Danielle and Prasanna, for taking time today and speaking to us and telling us all about simulation and MathWorks solutions and how you are supporting OEMs brace electrification with more precision and more confidence. Thank you so much.